Welcome to I Eat Physics for Breakfast.
Hello everyone, this recorded video focuses on the discussion of the properties of visible spectrum, which is part of the electromagnetic spectrum. So when we say electromagnetic waves, so this is actually a term used to refer to the type of wave which contains the interrelation of our electric field or electric charge and magnetic field. So this particular type of wave is produced because of the vibration of a particle we call the photon. So this type of wave is classified as transverse wave. So we classified it as transverse wave because of the direction of the propagation is actually perpendicular to its production. So this particular type of wave can travel even in empty space or in vacuum. Okay, so when we speak of electromagnetic waves, there are actually different types of this particular wave. So we can classify it depending on its characteristic, particularly its wavelength, its frequency, and its photon energy. So these different characteristics are reflected in what we call the electromagnetic spectrum. So when we say electromagnetic spectrum, this is a continuum or this is a range which shows or reflects the different frequencies of electromagnetic radiation and their respective wavelength and photon energies. So if you will actually analyze it, it is a range from left to right, starting from left, the one with the, depending on the orientation, but usually starting from the left with the longest wavelength, which is the radio wave, up until the short wavelength radiation, which is the gamma rays. And since this wavelength is actually inversely proportional to the frequency, so that's their relationship, okay? So we can infer that their frequency, so the one with the long wavelength, this type of radiation, let's have the radio wave as an example. It means that they have low frequency, okay? And the one with the short wavelength, let's say the X-ray and the gamma rays, they actually have a high frequency. So again, the relationship between the wavelength and the frequency is actually inversely or indirectly proportional. So that will actually be very relevant to the equation that we will show later or we will discuss later as we go along. Okay, so from that description, we can say that visible light is actually just a portion of this electromagnetic spectrum. So when we say visible light or visible spectrum, we are referring, this is a collective term which refers to the type of electromagnetic wave which is visible to the naked eye. Okay, so later on we will be focusing on this particular type of radiation. And from the visible spectrum, we can say that since they have different wavelength, they have different energies, they have different frequencies, each type of radiation has its own use, its own advantage and disadvantages. Okay? So I might give a separate video which would discuss the importance of this varying types of radiation to our daily life. So let's focus on our next, on the next part of the presentation, which is we would discuss specifically the speed of visible light. I have already mentioned a while ago that electromagnetic wave has a constant speed and they can travel even in a vacuum. So the speed is given by 3 times 10 raised to 8 meter per second. Okay, but to be more exact, so this is how you can actually compute for it. So this is just a trivia. If you will get your calculator, so if you have a scientific calculator with you, so just divide, the speed of light is equal to 1 divided by the square root of the product of two constants. We have the first, the electric constant, which is shift constant 32 times the magnetic constant, which is shift constant 33. So if you will evaluate this, you would actually get the exact amount of the speed of light, which is 299,792,458 or 299,792,458 meter per second. So as reflected on the table, you have there the summary of the wavelength, frequency, and energy of the visible spectrum. So we have there, for example, the violet light will give us a wavelength of this particular range, which is 380 to 450 nanometer. So if you will check the frequency, that will give you 668 to 789 terahertz. Okay, so how do we check if this particular value is correct? And how do we use the equation? So the useful equation that would actually help us determine either the wavelength or the frequency of a particular electromagnetic wave, is this. So the equation is the wave speed is equal to lambda, or the wavelength, times frequency. Okay? So again, the wave speed is equal to lambda times frequency.
For sample problem number 1, the question is, what is the frequency of a green light that has a wavelength of 5.5 times 10 raised to negative 7 meters? Just like our usual approach, we will write the given. So in this sample problem, we have the lambda, or the wavelength, which is given to be 5.5 times 10 raised to negative 7 meters. Then it's not written here, but it's implied that we will use the concept of the speed of electromagnetic waves. Therefore, since we know that the speed of light, or the speed of electromagnetic wave, is constant, in vacuum, we will write V. So V is just equal to 3 times 10 raised to 8 meter per second. So please don't be confused. We just use the letter V as a notation to be consistent with the equation. But this is also equal to our constant, which is the speed of light. Okay, so since we're looking for F, for the frequency, we have to derive our equation. The equation that was presented to us is V is equal to lambda times frequency. So in this equation, we can see its relationship, or its connection to what we were discussing a while ago. So we said that since the speed of light is constant, and the relationship between lambda, or the wavelength, and frequency is inversely proportional. So if there is a decrease in the wavelength, let's say, there should be an increase in the frequency to compensate, so that when we get the product of these two different variables, we will still arrive with the same amount of velocity, or speed of the electromagnetic waves. Okay? So let's proceed with our main objective, which is to get the equation of frequency. So frequency is just equal to velocity over lambda. So from here, we can just input the values. 3 times 10 raised to 8 as the meter per second as the speed of the wave divided by the lambda or the wavelength, which is 5.5 times 10 raised to negative 7. This is in meters. So you can now compute. For the units, we will cancel out meters and we will be left with 1 per second as the unit, right? So if you input this to your calculators, it will evaluate this. You will get 5.45. So this is 5.45 times 10 raised to 14. So raised to 14, this is per second, which is again equivalent to hertz. Okay, so if you want to rewrite it, let's use the engineering notation. So from 5.45 times 10 raised to 14, the closest we can use is the tera, which is equivalent to 10 raised to 12. So this will be equal to 545 terahertz. And this is now the frequency of our green light in vacuum.
Okay, so for sample problem number 2, the question is, what is the wavelength of a blue light with a frequency of 600 hertz? Terahertz, rather. So if you would like to answer this on your own, please pause the video, then continue whenever you're. F is equal to 600 terahertz. So that's 600 times 10 raised to 12 hertz, which is also equivalent if you want to write it in a proper scientific notation. 6 times 10 raised to 14 hertz. Okay, so this is the frequency. Now, again, it's not indicated here, but we know that the speed of light is 3 times 10 raised to 8 meter per second. And since we are looking for the wavelength, so we have to look for the formula, or we have to derive the formula. V is equal to lambda times frequency. So if we are interested on the lambda, therefore, lambda would just be equal to speed over frequency. So by just writing the given, we have the speed, which is 3 times 10 raised to 8 meter per second, and your frequency, which is 6 times 10 raised to positive 14. This is per second. So if we evaluate this, you will get 3 times 10 raised to 8 divided by 6 times 10 raised to positive 14. You will get 5 times 10 raised to negative 7 meters. And this is equivalent to 500 times 10 raised to negative 9, right? So that would be 500 nanometers. Okay, so this is now the wavelength of our blue light. If you have questions or clarifications, you may write your comments down below.